Hey everyone, I'm Dave Ojha. Today I'm going to be talking to you about lowering the confirmation times in consensus. The goal of this talk is basically for the topic of when you go make a transaction on a blockchain, we want to minimize the time for a front end to update. Like, if you ever even use Ethereum, you need at best a minimum 15 seconds, but often like minutes to get a UI update. In Osmosis, we've recently lowered the block time from like 6 seconds to 2.5 seconds, and it already feels way better. But the Web 2 experience we want here is you click a button and you get a response immediately. So when you're talking about how do we make this happen, and why am I talking about this? It's because we've been spending a lot of time in Osmosis trying to figure out how to lower the block times to improve the UX of this stuff. Adam gave a talk yesterday talking about a decent amount of this, and today I'll be chatting about the consensus side. So first off, apologies everyone. This talk's going to be a little bit less polished. I decided to rewrite it entirely this morning. The prior version was too complicated. Hopefully it's going to be simpler, but I think it'll be fun and we'll all learn some new things. So the idea of it first is we're going to talk about what are we aiming to improve in consensus today, then a brief overview of where Tendermint's at, both the theoretical minimum and the reality of today. We'll talk about why short-term censorship resistance is important and pre-confs, and then talk about some ideas where there's a unique idea in Cosmos for we can get a lot of scaling by doing things in the mempool within every validator. But this is like one example is DEVMOS memclub. It's like actually a very pioneering, cool thing. But the problem is you lose your confirmation time, this like reliable UI update. And so we'll talk about how we can use provable DA ingestion to get UI update confirmation times back, and then globally geo-distribute DA layers and get down to 50 milliseconds again. And if we have time, describe like MPC mempools and Suave and how this gives you newer commitments. But let's dive into it. So what's our goals in consensus right now? The big problems we have is give people lower confirmation times, get high throughput, and get short-term censorship resistance. Now, if you think about it for a second, this is actually all the same problem. You go to Osmosis front end, you do a transaction, you want to get it in quickly. So high throughput is get me in quickly when there's many other people who want to do something right now. Short-term censorship resistance, get me in quickly when the next block proposer doesn't see me for whatever reason. Like, they choose to censor me. So first, let's talk about what's a commitment. So high level, a commitment is, I have a commitment to something when I know either this thing will happen, or if it doesn't happen, someone gets slashed, or some security assumption's broken. Later in this talk, I'll talk about some non-slash use cases, but warm up, you get included in a finalized Tendermint block. That's a commitment that your transaction's finalized, or 1/3 of stake is double signed and they get slashed. So the two types of commitments we care a lot about is first inclusion commitments. So this means that your transaction will be included in a block. And for some things, this suffices. If I go to place a limit order, I just need to know that this will be included. And that's enough for a UI update. The update for did it get cleared or not is a second process. But then some things need execution commitments. So this means that I know the state result after doing the thing. So for instance, I want to spend $100 buying Bitcoin. I like market buying it. I want to know how many Bitcoin did I actually get out at the end of the day for my UI update. So these are the two main types of commitments that we're going to be concerned about. So warm up, what's going on in traditional Cosmos chains? Well, your latency is your time to get into a finalized block, but turns out you actually have no guarantees for how long that's going to be. Like I'm sure everyone here is familiar. You've made a transaction on the front end, and it gets stuck in the mempool. Who knows how long, and you have no idea when it'll land. If we assume sufficient fees and the mempool is working nicely, then this time is at minimum like one final block time. But we don't actually know this, so it's not a hard guarantee. One cool thing about Cosmos, it's maybe unique amongst other chains, is that you have one block finality. So when you're in one block, once you're one block in, your transaction's final, versus like Ethereum, this is 2 epochs or 30 minutes most of the time. And Solana, I forget how they parameterize it. I think it's like around 50 blocks at like 200 milliseconds per block. So Cosmos is unique in this regard. All right. And then first I want to brief interlude on what's censorship resistance and why we care about that before we get into time measurements. So remember, censorship's the word we use, but this refers to a couple things. Like, first off is the validator, like the next block proposer, denying they saw my transaction. They can just pretend to ignore whatever they want. There could be legitimate network delay. It's not always adversarial. Like, it's actually true that sometimes I talk to a server and the packets just aren't making it there. And an important thing here is software bugs and implementation differences prevent transactions from getting through. But this is a large class of problems we care about. Like, we're going to have 3 strategies for lowering censorship resistance, or X4. One big one that I think is under discussed is just making blocks faster, because that means you have that means that it's easier to get to the next proposer who will include you. And conveniently, faster block times are also going to be a big part of getting faster commitment times, because you proceed at the rate of the blockchain. Then the second biggest one is breaking up the proposer monopoly on block space. Don't just have one person getting to choose what is the next block data. And the third and fourth ones are encrypted mempools. I'm not going to spend time on it in this talk. See Fervio and like Sunny and I's past talks on threshold encryption. And this actually already depends on breaking up the proposer monopoly, or you have to assume a very centralized system, or like some magic crypto called witness encryption that we previously thought was very impossible. There's a first paper, we don't know if it's going to be broken yet or not, that came out this March that might make that real like sometime soon. But and then there's we can use app layer incentives for censorship resistance. But in this talk, just faster block times and breaking up the proposer monopoly. So why is this important? Well, a lot of things you want to do have time urgency. So anything that depends on a challenge period already has time urgency. Because you have to get the challenge on chain. If you have a credit account like margin, and it looks like the price is about to get liquidated, you want to get a transaction on the chain quickly to top up your balance, so that you know that before like a price moves against you and you get liquidated. This is an important property. Or conversely, if you're the lending market, you want liquidations to process quickly so you stay solvent. So you want to make sure you can get into a block. Another important thing is on-chain TWAPs are actually only as good as your censorship resistance. So in Ethereum, like we used to talk about 5-minute, 15-minute TWAPs for like just how you get spot price. This is on Ethereum mainnet. This has actually gone out of fashion because you routinely have one block proposer. Coinbase, multiple, but Coinbase is one example, proposing 8 to 10 blocks in a row, which means that they could, in principle, prevent like proper arbitrage getting in. They can control at spot price and ruin your TWAPs. So it's the same thing as SexDex arbitrage. So we do care about this a lot. Now, is this so bad? If you think about it, if T% of proposers are censoring you, like 30% of people are censoring you, then actually within 2 blocks on average, you should still be able to get in if the mempool is like working well. And if over 33% censor you, you're kind of screwed. Encryption gets you to 2/3, but this is actually not true, because that's only the average case. It turns out that we have to look at the probability of someone proposing 8 blocks in a row, someone proposing 10 blocks in a row. So like on Ethereum, with Coinbase controlling like 15% of stake, this could happen like 0.1% of the time. This isn't good enough because we need to have short-term censorship resistance when like more guaranteed better than 0.1% of the time. If that 0.1% happens during a black swan event, a lot of people could be screwed, or it's a lot of MEV opportunity that this is an unsound system. So our first biggest protection, speed up block time. So Ethereum block time, 15 seconds. So 10 blocks, that's 2 minutes. Well, if we look, we just went to the Osmosis Neutron current block time of 2.5 seconds. That same proof of stake threat model takes you to a 20-second censorship delay, which is a massive improvement. But now let's go into what is Tendermint today. What do our block times and like confirmation times need to be? Well, Tendermint is a consensus protocol with 3 rounds of communication, 2 rounds of voting. So what this means is a block proposer wants to choose a block. They have to go tell this block to everyone else in the network. So that's 1 internet latency. Then they have 2 rounds of voting. So best case, like everyone receives it at the same time, does another round of voting twice. So yeah, propose, vote once, vote twice, 3 latencies. So global internet latency, for this talk, I'm going to say it's like 150 milliseconds. It's speed of light guarantees. We're a bit worse than speed of light because we have to use fiber optics cables. And it turns out that going from North America to Australia is nowhere near the optimal you'd expect. There's a lot of weird routing going on there. So 150 milliseconds. But our globally distributed best case then is for Tendermint's 450 milliseconds. Oh, something I forgot to note in the beginning of the talk is all of my timings I'm concerned about we're making globally distributed consensus, because that's like the interesting scenario of very robust decentralized protocols. So what's the user confirmation time for, because remember I said before that inclusion and execution today in Cosmos is getting into a finalized block. Well, okay, time to finality is 450 milliseconds. And then the user has to talk to the next proposer. That's another global internet latency, so another 150, so 600. But then they have to know the 2/3 pre-commits from anyone who's near them. So that can be much quicker, say 50 milliseconds. So 650 millisecond user commitment times in the best case. So if we have the protocol as let's round up 450 milliseconds to 500. There's some delays going on. On the 10 Coinbase example, takes us from Ethereum 2 minutes to already 5 seconds. That's actually extremely good. We can even pipeline consensus rounds to make like a new block happen on average every 200 milliseconds. Then that takes us 2 minutes to like 2 seconds-ish. Great. But I don't know, some of you might be pausing here of like, no Cosmos chain is actually the 500 milliseconds, especially no globally distributed one. And on Osmosis, we measured it 2 months ago, and the consensus time was actually 1.3 seconds. This is actually just like software bugs. We'll improve all of these. Been going through a bunch of these with many folks from Informal and Celestia, and it's all fixable. In the last month, like we've already gone from 1.3 seconds on Osmosis to, if you use the latest patch, 1 second. I fully expect with like fixes we keep on finding to make this get another 200 milliseconds off in the next month. Like to give you an idea here, like a lot of the time is just simple bugs someone has to look into. Like we saw that we'd verify a commit 4 times, like sequentially. One of the big improvements, do that once, speed up the commit verification time, like 2x. That on its own dropped 100 milliseconds. Another thing we found was updating the mempool after a block was blocking you voting the next round. Just go fix that. Another 50 milliseconds saved. Like this is not it's just bugs we're going to get through. I'm not going to dive into this too much, but Adam hit on yesterday that like block time in Cosmos also has this like time.sleep called timeout commit. And as we keep improving other CPU improvements and the same stuff, we'll drive that down. You can go see Adam's talk recording for more details. Or another Matt's talk is also like a big on IVLv2 is another big contributing factor for like letting us lower this. But yeah, software improvements, we'll get down to this theoretical minimum. So it's like think about the minimum first and achieving that. So okay, now we're getting to the meat of the talk. The first thing I want to hit on is this like kind of new idea of, to date, we've been confirming user transactions when a block is finalized. Here I want to claim to you that we can actually do this when we see 2/3 of people pre-voting on a block. So pre-voting is the name of the first round of votes. So if I see 2/3 people pre-vote on a block in Tendermint, there's only 3 conditions in which this block is not going to be finalized. Either people are double signing, people stop being honest in ways that can't be attributable, or the global internet has been like partitioned. So global internet partitioning is a very like strong assumption. This is probably never going to happen. This means that no one in North America can like communicate to anyone in Asia. Like there's so many ways packets are routed. This is very unlikely to be violated. Like you've got deep sea fiber, Starlink, whatever DSL is properly called, etc. So it actually is the case that when 4 years ago we were considering changing the parameterization of like, consensus protocol is to not be at one, to be like partially synchronous, because we thought this is never going to be hit. So 2/3 of validators pre-voting is a strong signal that for most UIs is sufficient for updating. So if we did this, what's our delay going to look like? Your user talks to the next block proposer, or it gossips, next block proposer, and then we have 2 rounds of voting, and then whoever's the closest node talks to them. Like, we basically shave off 1 internet latency, 500 milliseconds of time to confirmation. That would be quite fast. This would be a very nice user experience. There's some discussion, actually I just discovered this yesterday, so I thought I'd throw this in. You could achieve 1 round VFT consensus. It's actually a long line of work doing this. We don't need this, because using getting us guarantee off of pre-votes is actually the same thing, the same latency. So we should just switch to, we can stick with Comet and just engineer UI confirmations off of this pre-vote phase. Next I want to talk about proposer commitments, or otherwise called like pre-confirmations. So the idea is that imagine a user can gossip the transaction to the next block proposer. Then the proposer can just sign something to them, promising that I'm going to include you in position number 5 in the next block with these transactions before you. If I violate the assumption, aka like I propose a block that doesn't satisfy this, then slash me. And so now your latency or your communication flows, the user talks to the next proposer, they get something signed back to them, and 1 global internet round trip that so can be quite quick. Problem is, this isn't actually a great guarantee. So this has reliability issues. Like, a block proposer's block can just not be chosen. They could just, their internet could not be good enough, etc. In Cosmos, we have some empiric proof. This is basically every time you go to round 1 or round 2 in a blockchain, in any chain in Cosmos. And turns out this is actually pretty common. This is, I don't have exact numbers, but like hand waving me checking mint scan like millions of times over my life. I'd say this is like 1 to 5% of the time. This is so that's a terrible user guarantee if if failed 1 out of 100 to 1 out of 20 times. Rollups are doing this in Ethereum, and they get away with this because they're centralized. There's some that are doing decentralized consensus, but those are the ones giving you these pre-comps. The ones who are centralized get away because they're the only person, they get a monopoly on block space, which is a problem. And also, if you want short-term censorship resistance, your pre-confirmation guarantee that won't give you execution commitments. Because the idea of getting short-term CR is that we're going to need more people contributing to your block data, which would then prevent execution commitments. So pre-comps can only be used for inclusion commitments in this case, for any like DeFi application. So in summary, a pre-comp traditionally gives you 200, 300 millisecond guarantees that aren't so good in when you're getting decentralized consensus, and won't give you execution commitments. But here's this cool idea where we can change this up a bit. We can actually get execution pre-comps from someone who isn't the next block proposer, or that becomes useful. And this will map onto the notion of intents, if you're familiar with them. So a user wants to buy Bitcoin, and they send this transaction to the mempool. Then some market maker sees it, and then can send a signed thing back to the user. So now this flow can happen in 50 to 100 milliseconds. So what could we do here to give the market maker a guarantee to the user that they'll believe? Well, the market maker can say that I will clear your trade at this price, basically like some price that you're satisfied with in your transaction. I'll clear your trade at that price, and this will get on chain within the next, say, 10 blocks. If such a transaction isn't on chain within 10 blocks, slash me. So this means that so this flow can happen if there's such a market maker, or you can. This is just very geosynchronous, like North America communication. So 50 to 100 milliseconds or less. So what are the guarantees we have to be concerned with? There's 2. The market maker the market maker just gives you the signed thing that gives you the UI update, that lets you make a UI update, and they don't meet it. Then we just need some automated protocol to do the slash, and then that will satisfy the original intent anyway. So the second thing you need is if there's no such market maker. Well, then what you do is you just fall back to posting on the chain. If no market maker does this, post on the chain, pay a slight transaction fee, gets 500 millisecond thing. So now users can optimistically get this 50 to 100 millisecond guarantee if such market makers exist. Otherwise, fall back to the full chain. So it's, I don't know, to me, very cool. We can actually push this pre-comp stuff with better guarantees by making it not consensus's job, by going to external actors. And this actually works for a much wider class of things than just trades. And a very important feature is not overloading consensus, because it lets us scale, have multiple teams do stuff, etc. So great, one approach to getting 50 millisecond legitimately Web 2 times. Now I'm going to switch gears a little bit. Sorry, I know I've been going a bit fast. Into how we use vote extensions for censorship resistance. I'm actually not going to diagram out vote extensions. We've had 2 great talks on this already, one from Skip this week. But a vote extension in principle is just, in the pre-commit phase, every validator can contribute block data. So we can get censorship resistant inclusion guarantees using this. If I'm a user, I can send a transaction to 34% of stake. If they all give me a inclusion commitment, like a pre-comp that they've seen this, then I know that I will be included in the next block, and I've removed the dependence on the next block proposer. Shout out to the Skip folks, their top of block auction work is actually exactly this in Osmosis. Right now it's pre-vote extensions, and soon we're upgrading to having vote extensions, and it'll be live. So very exciting. So what's the latency of this? It's actually the same latency as normal pre-comps in the non-decentralized case. So we have a single, we just trust the next proposer. There's one round trip to each validator, and you wait for the last one to send you something back. So one internet round trip to 250-ish seconds to 300 milliseconds, 250 to 300-ish milliseconds. So we don't actually pay more latency for this. Just you have to engineer communication in fee markets, and you now have a robust guarantee. So using pre-comps with vote extensions is going to be very powerful. I'll interlude here where I often talk a lot about Bullshark, where I think of Bullshark as just vote extensions. You take the design of vote extensions to the optimum. You have Bullshark's basically in every tenement round. Vote extensions are you add extra data to pre-commits or one round of voting. Bullshark, every validator is always proposing new data, and every vote includes links to the rest of the data they saw. So you already have the vote extension level grade censorship resistance, because every vote must link to show the 2/3 of votes in the prior round they saw. And something I haven't talked about is kind of the data pipeline for when opportunities are available, when is our vote extension available. But Bullshark's kind of already achieving this optimal thing. So I imagine this is the end state of vote extensions. After we iterate a couple more times, as we need more lower and lower latency, we'll get to here. And so one cool thing is it makes pre-comp strategies always available, and you get this property of if I talk to any block proposer, or if I talk to any validator, once I see that their vote's been seen by 2/3 other people, well, I know I'm going to be included. So this actually will drop the latency timings. Yeah, I'm excited for this, my bad. It'll drop the latency timings where your first connection from user to proposer was internet round trip. Now that can actually always be local as well. So now take all latency timings we've seen in the talk and drop one more internet, global internet round trip to now being a local round trip. So another 100 milliseconds saved off all user comps. So very cool. I think of this as the end state after we iterate much more. Okay, so now the next big point I want to hit on is throughput of a cool thing we've done for throughput. We're pioneering Cosmos for throughput improvements. So this idea I hit on the roadmap slide is that we have this desire to make validators do a lot. For instance, DOEDX's memclub is basically having every validator run an in-memory order book And then when they propose a block, they include matched orders. So this is great because it really improved throughput. It's bad because every validator has full MEV rights. So what are things they can do? You've placed a limit order. You want to cancel it. They can just pretend to ignore the cancel, each validator. Or you do a market order, like I don't know, I want to buy $1,000 of Bitcoin, and the validator just pretends that they never saw any limit orders that you'd hit, so you get a really bad execution price. These are big problems. So now you have this issue of if you're a user, you send a transaction to the network, you actually have no idea if it'll ever be in, because you have no idea if validators will include you in their view. It's even hard to imagine like a pre-comp system here, because in a pre-comp system, you'll know that like the validator you talked to saw it, but not the rest of the network. So there's no shared view of the data here. So this is quite problematic, but it turns out we can fix this. Okay. Well, first off, let's trade off here. The throughput is much faster because we're doing everything in memory, only posting cleared things onto the chain. Our censorship resistance is like 0 or worse than normal blockchains because things are only cleared, only matched things ever get in, and everything else can be ignored. We've lost user latency or confirmations. So when you do a UI update, you're doing this your confirmation as a user is you've talked to one RPC or one validator, which is, as I hit on earlier, is a very weak guarantee here. So we can improve this though, and we should improve this and use this throughout like more of Cosmos. So we can get this throughput optimization by having this thing I'm calling provable DA ingestion. So DA first is data availability. So what's going on? Every user transaction we're relying on every user transaction being seen by all validators. But that's effectively a data availability guarantee. So why didn't we just put this in the block data originally? Well, we could. We could say our original chain also does DA well, or we could try to separate concerns. But imagine we had the system where we bulletin board post all user orders somewhere, and then every validator says that, hey, I promise that I've seen everything in this DA layer, or like everything in this DA layer has been included in my mempool, and then when I post my matches, I'm gonna we can either be optimistic or ZK arguments or just SGX arguments say that I've processed everything, and without ignoring stuff, I've done all of my matching correctly. So, sorry, that was a bit rough. Okay, so every validator knows you've seen every limit order that the market buy should hit, and every cancellation is guaranteed that you've included as long as it's gotten that DA layer. So as a user, you know that you're confirmed once you get included in the DA layer, because now every validator will then see you at some latency. So your user confirmation time is basically going to be DA layer inclusion time, which is just Tendermint time, plus DA layer inclusion time, plus like some propagation delay. So let's say 1 internet round trip above that. So why a DA layer? Again, we need a shared view of this data. How do we improve this though? Like, can we get better than 500 milliseconds and this throughput guarantee? And what's cool is we can. We can imagine we have geo-distributed DA layers. So we have a DA layer in every single region of the world. So like imagine you have a North America DA layer, Europe DA layer, and Asia DA layer. As a user, you talk to the DA layer that's local to you in like 50 millisecond timing. That DA layer achieves consensus very quickly because they're all nearby each other. And you have a sync protocol where different DA layers, like the Europe DA layer, must ingest a North America DA data with 100 to 200 millisecond delay. And so if we do this, then we can make every validator have this guarantee that you must fetch data from your local, your very recent block in your local DA zone. And then, and because of the sync protocol, we know that your local DA layer will have data coming from every other region at like the internet, the fiber optics delay times, 100 to 200 milliseconds. So this means that as a user, you can talk to your local DA layer and for an inclusion guarantee. So that's going to take you like 50 milliseconds-ish. And then, so you talk to your local DA layer in 50 milliseconds. And so you have an immediate confirmation in Web 2 timing that any proposer that's nearby there, or who's next, will include you quickly. So, and then this guarantee keeps improving as just wait latency. Like 200 milliseconds later, it should be in every other DA zone in the world. And so, within so you can look at the proposer schedule, see when the next proposer is, to know should you get a UI update in 50 milliseconds to 300 milliseconds. This is a great end state of high throughput and quick user confirmations for inclusion. And actually, because this system is also considered like limit orders and market buys, it actually extends to execution for some. It works for sure for inclusion, and if you're like very careful, things also works for some class of execution. So I think hitting time-ish. So outro of this, what I think Cosmos should do. Well, first I think we should engineer Tendermint. Like let's get some more collective effort on like high load testing the stuff and improving like software bugs and adding some features in to get us to the theoretical minimum of 3 internet latencies for Tendermint block times. Then just keep on iterating on vote extensions for getting better short-term censorship resistant inclusion, so we can use this stuff for more things, and encrypted mempools. And then let's shave off one more internet round trip by using the pre-vote phase, not finalized blocks. And then let's get to this like mad glorious end state of 50 millisecond confirmations via geo-distributed DA layers, and like having every validator go to some provable DA ingest. What's kind of cool is we also don't need every chain to reinvent the wheel here. If DA was good enough, you could use any chain. And so we have this flexible trade-off of spin up your own DA layers or use this one highly secure idea. This is the idea of both Celestia and ETH 2.0 dank sharding. Then after that, we can consider pipelining Tendermint or doing Bullshark. It's just like very cool long-term improvement, and pre-comps with vote extensions. That's my proposed thing. So yeah, let's chat on how to improve it, especially if you're like focused on Tendermint improvement stuff. So thank everyone for your time. And yeah, if you have any questions? I know that was buried in the weeds, so I hope there's questions for things I can explain better.
Okay, I have a question.
Yeah.
Can you speak to, with respect to pre-confirmations, how you think about liveness risk? So the way I'm sort of imagining this risk is, suppose you've got a limit order out there, some event happens that makes that limit order tasty, people all over the world are suddenly saying, I want to match this, go out to their local nearest validators, they get pre-commits, right? Now you potentially could have an irreconcilable set of pre-commits and the necessity that someone gets slashed on the next block. Because you actually can't reach consensus. Too many people have been promised this limit order by too many different validators. Like, how do you think about a risk along the lines of basically a liveness risk there?
So I think what you do there is the guarantee validators can give you is, the only guarantee a validator can give you on their own is inclusion. Execution guarantees have to go to this separate market maker market, not tied into consensus. So when you're just doing inclusion, that's very reconcilable. Everyone can say, promise me that they'll include me, and this works out. So actually, in the pre-conf slide before, I did remove one sentence to I said that a proposer will give me a pre-conf that they'll include me as spot number 5 with these transactions before me. But I should have amended that to actually be, you'll include me at this spot unless your transaction hash got into a prior block. So if you use a semantic like that, that fixes it. Or if you're doing it in vote extensions and just doing inclusion, it's also resolved.
Okay, but you can still run out of space in a block. I mean, I still feel like there's a risk there.
Well, no, the idea is every validator has some space reserved in the vote extension-like system. And when you're the block proposer, you get to lay out your block data anyway. So when you give the promise, you know there's space. If there wasn't space and you gave the promise, that is your fault. There's no you just ran bad code. In some sense, you are like you signed a promise you can't fulfill, so therefore you get the slash. So yeah, there's no risk there under like correct code implementations.
Thanks for this talk. This was awesome. It sounds to me like the two contributions here are first smoothing out the sort of space of guarantees before a block, and then the second is pushing the short-term censorship resistance guarantees to sort of the edges of the network closer to where the users are. Most of the way you describe these topics were on sort of UI guarantees, but what we've seen in Ethereum especially is that anytime there's this commitment space, it gets hijacked and sort of dominated by like MEV or sort of like HFT equivalent stuff, right? Basically people using these pre-commitments to
do sandwiches.
To do sandwiches or for financial use case in general, and then it becomes too expensive for users to do it. So do you have any ideas on how we resolve that?
Yeah, so and the problem is we're trying to do stuff for swaps as well, so you can't really distinguish type of activity here. So that's interesting is, I didn't hit on this earlier, but like the DOIDX memclub example, when you do gossip in the mempool layer, there's actually no fees there, right? You only pay fees when something gets matched on chain. Why was that sound? There's some novel spam resistance guarantee. So we could imagine that one technique for this is like reducing, improving, like making more clever spam resistance guarantees. Like, I don't know, if you stake 1%, you stake 0.1% of supply, you get so many like free short-term CR commit options, like no fees. But then another space thing, but you're right. Like these can all, if the market has high demand, fees will go up. So we want to improve throughput really well, and then two, this is why I think getting block time lower is so key, because if we get block time lower while still being sufficient for full node syncing, your base case is a 500 to 650 millisecond bound, and so then like that's your worst case. I don't know. Does that make sense? Or, cool. Yeah.
Okay, so if you turn the DA each individual blockchains, right? If you make them single node timestamp signers, you get what I was trying to propose before. You don't need the DAs to be a set of blockchains or a set of validators, because the transaction signer, the user can submit their transaction to multiple DAs, maybe 5 or 10 random ones. And I think that will significantly reduce the latency in the whole system. And you can also get basically a global timestamp for every transaction. I think
that's an interesting claim. Yeah. So a global timestamp I'm concerned with, because that sounds a little bit like kind of the fair ordering claims, like in Wendy and stuff, where I think these kind of ignored adversarial behavior. But you're right that if you gossip to multiple judiciary DA layers, maybe you get better user latency guarantees. I hadn't thought about that. That's actually really clever.
Yeah, that's what I want to talk to DXDY about too. Let's get together.
Yeah, let's do it.
Yeah, thank you for the talk. I kind of have two related questions. So the first one is, so back, let's call it the high activity period on Terra, right? We were seeing something like 30 to 60 second blocks with huge amount of transactions in them. So as someone who's very familiar with consensus, but not necessarily our Go Tendermint implementation, how much of that has been like kind of looked at and improved upon since then?
I think this is like stuff that we've gotten fixed in the last so one big thing was literally yesterday, but then a lot last 6 weeks. So I can describe some of the problems. This is interesting. So one of the problems is after you were committed a block, you'd have to you have this mempool operation for updating every transaction, and we just there was a minor mistake that like everything was sound, but we would block updating. We would block proposing the next block or voting or doing anything on until we update everything in the mempool. Another bug we had was when you were doing any consensus phase, like executing a block or etc., we'd actually also accidentally block incoming packets. So that's the thing we've found in the last week, and so very easy fixes just required noticing it. So I want to benchmark load literally next week to see is there any new bug after those PRs get merged.
How many new ones?
Yeah. Well, soundness is like we haven't released a protocol, but like what's the next bottleneck? So I think that we've made an order of magnitude improvement on scaling since like Tendermint incident. The Terra Terra USDT peg. But now what's the next bottleneck? We need to try load and see what's next.
And then building off of that is you talk a lot about Bull Shark, but then there's also, all these new advancements in consensus like, Shoal and Mysticeti and Narwhal, obviously, and Motorware and so on. So do you think all these systems are things that we can, build Tendermint up to par with, or are these kind of things that deserve a look from the ground up and maybe a new?
The only thing I think that like potentially gets us is like bullshit or something DAG based. Most of these are DAG based things. Narwhal, no. Narwhal is actually just a mempool thing. But Bull Shark maybe. I still like think that the Bull Shark state machine is actually. You can imagine Tendermint as this like digraph based thing and get this graceful transition. But I would say that nothing besides Bull Shark seems just like potential justification for a rewrite. Bull Shark's the only idea I've seen that feels like it gets to this, and I think it's worth like actually specking out like what would it mean to include some Tendermint. Like we've actually done specs for pipeline Tendermint. Like actually not me, informal folks have done a great job with this, and it seems like you can get pipeline Tendermint in with no updates. So Bull Shark's like a nice improvement. I don't know if it's a rewrite everything. I don't know if it's like a next year long, 1 year out worthwhile improvement. I do think we fast forward many years from now, we do something DAG based. I don't know. We should examine this.
All right, cool. Thanks.
Hey, thanks for the talk. I found the geolocalized DA layer stuff really interesting, and you touched on how you can only really provide commitment to inclusion in that scenario. But I'm wondering if there's a way that you could partition state across the different local DA regions so that each local DA region is able to commit to the execution of transactions which only access the state that they are basically assigned for their partition.
So we can imagine that. I think that line of thinking is more so the sharding line of thinking of chains. My macro take is if we're splitting things by like what state you access, let's actually just go make independent blockchains. Like let's go make different full chains with either state execution, and then anything crosses the boundary, just go IBC it. So there's many things to debate on in this, but this is my macro take for like back when we were near sharding or like ETH2 sharding was the conversation topics. Like if you have a clean state partition, just go make different blockchains and IBC communicate.
Okay, I think I follow. But what if you could only provide an execution commitment if the transaction happens to only access the state, the subset of the state that's in your partition, but then when your transaction does access state across those boundaries, then you could only make the inclusion commitment.
That's fair. If you wanna minimize failure risk across different state partition boundaries, then my claim IBC on its own doesn't work. I think the space of cross-chain execution guarantees is pretty underexplored. I generally dislike bundling stuff into consensus for this and prefer solutions where it's like off-chain actors attempting to give guarantees, and those off-chain actors like rely on short-term censorship-resistant inclusion in both chains. Most things I think that the architecture of bundling consensus of two chains, of two like kind of independent states, is just going to lead to a lot of edge case like terrible latencies or like halts. But this is not well founded. Like someone could argue enough or show me like some proofs that they would think otherwise. That's my intuition.
All right. Any questions? All right. Thank you, Dave.
Yeah. Thanks so much, everyone.